I'd like to look at a collision between two billiard balls on a pool table. Now think about how we usually deal with collisions or explosions. We like to use the ideas of momentum. When we look at the track that the two balls take, it's very clear that this is not as simple as the momentum problems we dealt with in one dimension. Let's call this way the negative y direction. And you can see that we have negative y momentum at first because only the white cue ball was moving. But then we had a collision. And we still had negative y momentum in the cue ball, but now we also had it in this green ball. And we've also added in x. This one's moving in the negative x direction, this one's moving in the positive x direction. So we're going to try out our momentum tools, impulse and conservation of momentum, with this two-dimensional problem and see what we can get out of them. At first we're going to look at impulse, how we can describe how one of these two balls has had its momentum changed. We're then going to use conservation of momentum to describe this collision, just like we would a one-dimensional collision. We'll use the strategy we used with forces. We'll look at just the left-right component of each momentum, and we'll see if those are conserved. Then we'll look at just the up-down components of momentum and see if those are conserved. We'll continue with our idea of the independence of the two dimensions. In other words, what happens in x stays in x, what happens in y stays in y. And we'll see if momentum is conserved independently in each dimension. First, let's take a look at impulse, and let's use vector arrows to try to understand what happens with impulse in a two-dimensional collision. And let's just look at a graphical representation first. Let's say we have a ball. It's coming into a table with a momentum PO. It bounces off the table at an angle and leaves with a momentum PF. What direction has the impulse been there? Well, we have to find this using vector math. So if we just do it using our arrows, I think it's pretty easy to see what direction the impulse is in. We have PO going down and to the right. The opposite of PO, negative PO, will be parallel to PO, but going in the other direction. So if we want to do PF minus PO, we reverse PO, and then we add PO, negative PO and POF head to tail. So there's PF, there's minus PO. When we draw the resultant vector from the tail of PF to the head of negative PO, we see that the change in momentum, delta P, is up. So, not surprisingly, when you have something going down and right, and then later it's going up and right, the right part hasn't changed, just the up part did. And that's what this picture is showing us. So I've altered this screenshot so that both the cue ball, which is mass A in red, and the green ball, which is mass B in blue-green, both their information is showing on the screen at once. And what we can see is that the green ball, up to the time of collision, had no momentum in either the x or y direction. The cue ball had a little bit of x momentum. It was moving pretty slowly left-right. It had quite a bit of up-down momentum, y momentum. So essentially we're going to be checking how the momentum that the cue ball, the white ball, had originally is divided up between the two afterwards. And this is going to get complicated quickly. We're going to have to pay attention to the x momentum it had before, and then the x momentum it had after. And we're going to have to check the x momentum the green ball had after. We're going to have to do the same for y. What y momentum did the cue ball have originally? What y momentum did it have after? And what y momentum does the green ball have? So we're going to have to be super organized to keep track of all these different numbers. So the only thing that's tricky about this problem is keeping track of where the numbers are coming from. So I'm going to do two separate conservation of momentum problems, a horizontal and a vertical. And I'm saying that the momentums of the two balls before should add together to be the same as the momentum of the two balls afterwards. Momentum is mass times velocity, and I'm getting the appropriate velocities from these position time graphs. This red one, the velocity of ball 1 before. The orange would be the velocity of ball 1 after. This would be the velocity of ball 2 before, ball 2 after. and these top are all the horizontals. So those numbers will be the ones that go into the horizontal problem. The verticals, which are on the bottom two graphs, still go into the vertical problem. What we see is that momentum does appear to be conserved if you look at each dimension separately. Very close numbers in the horizontal dimension before and after. A little bit farther off in the vertical dimension. There are some errors here, assuming both balls had the average mass of a pool ball. Sometimes a cue ball is heavier. Also, the first data points right as things started to shift didn't really seem to be linear, so I wonder if the collision was happening faster than the camera could record. But still, pretty good agreement that momentum does appear to be conserved in the x dimension and in the y dimension. So since there was no momentum of the green ball beforehand, it is interesting to see that basically in both dimensions, each ball gets roughly half of the original momentum. That makes sense. They're kind of sharing the original momentum between them, and since they have about the same mass, we expect them to get about the same amount. That won't be the case if there's wildly different masses. So since momentum does appear to be conserved horizontally and vertically, it means we can use this strategy to answer questions where there's a collision in two dimensions. We have to be as organized as we are here. We have to do the conservation of momentum separately in each dimension. But if we do that, it works. So in the next problem, we're going to have two pool balls that hit each other. We know everything about one of them. It asks us about what happens to the other one afterwards. How fast is it going and in what direction? So in this problem, we have two billiard balls colliding on the table, the 4-ball and the 9-ball. They start with 9-ball at rest. 4-ball has horizontal velocity. There's a collision which sends the 9-ball up and to the right and the 4-ball down and to the left. So how do we deal with that? Well, just like we did with forces. What happens in x, what happens in y stays in y. We have one momentum problem for x, we have one for y. Notice there were two balls before and two after. So we have a term for each ball before and after. And we have that for x and for y. Notice the labeling here. We have M1 V10, M2 V20, M1 V1F, M2 V2F. We have the same in both x and y, but I put a little x on the x components and a little y on the y components. So how do you do it? Well, you take our non-x or y velocity, which is ball 1 at the end, and you use trig to break down its components, so V1Fx, V1Fy. So did a little triangle, cosine got me x, sine got me y. Basically, you solve each of these problems separately. Here I'm solving for V2 final in the x, here I'm solving for V2 final in the y. And then, once you have those, you just add them back together. So the way you find out what V2 is you just do the Pythagorean theorem. A squared plus b squared equals c squared. And that gets you the hypotenuse and the magnitude of the final vector. So 3.73. And then to get the angle, since you know the sides of the triangle, you just do inverse tangent, and that gets you the angle. So all in all, a two-dimensional momentum problem is just two one-dimensional momentum problems. You solve for x, you solve for y. You figure out what the components of the vector you want are in x and y, and then you add them back together.